This video is about some of the models that can be used to describe diode operation. This is the characteristic curve of a typical diode. Unlike resistors, capacitors, and inductors, which are linear devices, diodes are nonlinear. That means the curve isn't a straight line. Most of the analysis methods we have used in the past don't work with diodes. This is the equation, often called the Shockley equation, that describes a diode's current when forward biased. It has several variables. Is is the saturation current. Saturation current is typically in the range between picoamps and femtoamps. A diode's reverse leakage current is approximately equal to this. N is the ideality factor. N is typically equal to about 1 for an integrated circuit diode and closer to 2 for a discrete diode. Vt is the thermal voltage. As its name implies, it's dependent on the diode's temperature. At 25 degrees C, the thermal voltage is about 26 millivolts. Even if you know the exact value of each of these three variables, you still have one equation with two unknowns. The two unknowns are diode voltage and diode current. A second equation can easily be found, but it will be linear. Combining a linear equation with a nonlinear one to find a simultaneous solution is nearly impossible to do algebraically. An easier way to calculate the current and voltage of a diode is to use a linear model that approximates its actual characteristics. The simplest but least accurate model that we can use to represent an actual diode curve is the ideal diode model. Simply replace the real diode in the circuit you are analyzing with an ideal diode. A reverse biased ideal diode acts like an open switch through which no current can flow. A forward biased ideal diode acts like a closed switch. Current flows easily and there is no voltage drop across it. The resulting characteristic curve is shown here in red, superimposed over the actual diode curve. Although the ideal diode model is quick and easy to use, it isn't very accurate. The ideal characteristic curve is substantially different than the real one. Another one we can use is the constant voltage model. The forward bias real diode is replaced with the closed switch of an ideal diode in series with an opposing voltage source. This voltage source represents the voltage that drops across the real diode when forward current flows through it. It is usually about 0.7 volts for silicon diodes. When reverse biased, this model behaves like the open switch of an ideal diode. The resulting characteristic curve is shown here in red, superimposed over the actual diode curve. It is more accurate than the ideal diode and almost as easy to use. For these reasons, it is the most commonly used diode model. An even more accurate diode model is the piecewise linear model. It adds the actual resistance of the silicon in the diode to the constant voltage model. This gives us an ideal diode in series with an opposing voltage and a resistance. The resistance is usually between a few ohms and a few tens of ohms. As you can see, the red curve of this model matches the real curve even more closely. The resistance creates a slope that is not straight up and is more tangent to the exponential curve. The higher the resistance, the flatter the slope will be. Although this model is the most accurate of the linear approximations, we usually don't know the exact value of the turn-on voltage or resistance. Simply guessing what they are would be no more accurate than using the constant voltage model. Here's a comparison of the relative accuracy of each model. Notice how closely the approximated linear characteristic of each model, which is shown in red, matches the nonlinear characteristic of a real diode.